Okay, so let's look at one of the typical problems from 8.1 and 8.2 section. All right, so we have that alpha is 0.10. Our null hypothesis, and our first hypothesis is always the null hypothesis, is that our population mean is 70.2, and then the alternate hypothesis is that the population mean is not equal to 70.2. We believe our population is normally distributed, but we don't know the standard deviation. We attain a sample size of 78 with a mean of 65.3 and a standard deviation of 12.1. We want to find the critical value. Now, a lot of you have been having trouble finding the critical value for the test. So we're going to use a program called StatTrek online that is very easy to use and will give us accuracy out to 3 decimal places. Now, very important, because we don't know our standard deviation for our population, StatTrek uses the t-chart instead of the z-chart. Although this does fit our central limit theorem, since we have a large sample, we could use the z-chart. But they've been using the t-chart, which is why your critical values might not be turning up to be the same as theirs. So I'm going to go to the StatTrek website, and I've already got it open. And when you go to the StatTrek website, you'll see this little thing over here on the left like this. And we want to go down to the t distribution. Now, if you are in a later section when you're doing your proportions, you'll want to use the normal distribution, but we're going to use the t distribution. And when we click on that, we get this calculator here. All right, now the degrees of freedom are always one less than our sample size. So let me go back here. Our sample size was 78, so our degrees of freedom are 77. All right, so I'm going to put those into the calculator. 77. And then I'm going to put the probability. Now, if we have a less than for our alternate hypothesis, we're just going to enter this 0.10. Same thing if we have a greater than, but I'll talk about that in a second. But since we have a not equal to in our alternate, we have to divide this by 2. So if we divide this by 2, 0.05 is what we're going to put into our chart. Oops, sorry. Into our chart here. So 0.05 gives us negative 1.665. All right, now, since this is a not equal to for the alternate hypothesis, this is a two-tailed test. So there's both a positive and negative critical value. There is 1.665, and I don't have to put the negative because it's right here in front. Positive and negative 1.665 are my critical values. To get the test statistic, I'm going to do the z-score formula we've seen before. All right, but it's really going to be a t-score since I use the t-test here. All right, so we're going to do, and there we go, x bar minus the mean over the standard deviation divided by the square root of the sample size. So our x bar back in our problem was 65.3, and our mean, our population mean was 70.2. So on top, I'll have 65.3 minus 70.2. Now I want to divide this by my standard deviation divided by the square root of the sample size. So let's see, let's look back. Standard deviation was 12.1, sample size was 78. All right, so 12.1 divided by, oops, let me do this. 12.1 divided by the square root, and I'll just do this rather than it taking forever to look up the symbol for it. All right, and I'll put that thing into my calculator. Now, I like to do the top first and the bottom second to make sure my calculations are right. So the top gives me negative 4.9. The bottom gives me 1.3700555211. And then my final calculation is going to give us negative 3.57649. And I could keep going with my decimals, but I'm sure we don't need as many for our answer. So let's see what we need to round off to. We need 3 decimal places. So that's going to be negative 3.576. All right, now let's just note our critical values, and I'm going to draw them on, very badly, but I'm going to draw them on a paint chart here. 1.665 and negative 1.665 are our critical values. So I've got this picture. This one's a left-tailed test, but let me go ahead and draw a right tail on it as well. All right, so we can think of the left side over here as negative 1. I can't draw very well on this. 6. Is it 665? Yeah, 665. 5. You just have to sort of imagine that that's a 6. Trying to draw on this with the cursor is not easy, and this is positive 1.665. Ah, not very good. All right, but anything to the left in this red region over here of negative 1.665 is in our rejection region, and anything to the right of 1.665 is in our rejection region. Okay, so our critical value, which was at negative 3 something, is definitely over here in this rejection region. All right, so with that in mind, the test statistic is in the critical region or the rejection region. Okay, so any test statistic that's in the critical region or the rejection region tells us to reject the null. When we reject the null, that means that we're going to consider our alternate hypothesis to be true. All right, so if the alternate hypothesis is true, let's look down here and see which statement coincides with that. There is sufficient evidence to warrant rejection of the claim that the population mean is not equal to 70.2. Now that's saying that our alternate is false, which is not what we're saying. We're saying our alternate is true. Okay, so it's not that. There is not sufficient evidence to warrant rejection of the claim that the population mean is not equal to 70.2. Well, that's true, but let's see if there's a little better answer than that, because we really want to say, hey, we've proved our alternate. The sample data support the claim that the population mean is not equal to 70.2. There it is. That's the one we want. Our data supports the claim that our alternate not equal to 70.2 is true. So we are going to grab this one. Now, just to be sure, let's just read the last one. There's not sufficient sample evidence to support the claim that the population mean is not equal. Now, no, you can't see that. Not equal to 70.2. No, that's the opposite of what we want. So the hardest part once you've gotten through here is deciding which one of these, because the wording on these is a little bit difficult. All right, and then we just hit submit. And we got it all. Okay. Now let me mention one further thing as you're doing your 8.3. 8.3 is exactly the same. Oh, let me mention something else before I do this. I mentioned that if this alternate was a less than, all we have to do is when we put our probability in here, we just put the probability as is, whatever alpha value we're given. We saw with the not equal to that we had to divide it in half before we put it in here. If it's a greater than alternate hypothesis, we can put it in the alpha as is, but it'll give us a negative score. What we need, though, for a greater than is the positive score rather than the negative t-score. So that's the important part if our alternate is greater than. Now, when you do 8.3, it's not going to ask you for a critical value. It's going to ask you for a p-value. To get a p-value, let's do a p-value for the test we just did. When we did this last one here, we got for our test statistic negative 3.576. To get a p-value, let's just take negative 3.576, go to the stat trek, and put that in. Now, I do need to get rid of this stuff that's in the probability box. All we do is we put this in and our degrees of freedom. This is always our test statistic, and hit calculate it, and there's the p-value, 0.0003. Now, since this one was a two-tailed test, for two-tailed test, we have to double the p-value. So this really would end up being 0.0006. For a one-tailed test, our p-value will end up being what we got right here. All right. Now, for a less than, I should say for a one-tailed less than, our p-value will be what we get right here. For a one-tailed greater than, the p-value that we get, we have to subtract from 1, just like we did when we were doing greater than probabilities before. Hopefully that clarifies things a little bit, but if not, just shoot me an email.